Back. Let's try another one of these examples. And in this case, I actually didn't close the interface because I wanted to show you one more thing. Let's look at one of the NeXus examples. So I have here a demonstration from measurements that we did on our instrument, the mouse. And this is a measurement on a metal organic framework powder. So we packed powder between two pieces of sticky tape. This is the scattering pattern that we got out. We actually have some wide angle diffraction in the wide angle range as well. So if we go into the data settings, you now see that the data settings we have are for reading in this particular NeXus file. So instead of giving the CSV load parameters, we now give it paths in our HDF5 file to where the individual datasets exist. And you must have Q intensity and the uncertainty on the intensity. We are still working on implementing units. So at the moment, Q is assumed to be in nanometers. The intensity is supposed to be in reciprocal meters. That is, of course, only important if you are interested in absolute volume fractions. Otherwise, it doesn't really matter whichever one you use. I have also cheated a little bit here. So I have set this parameter. This is the minimum uncertainty. So when we do the rebinning, right, when we get data, we always rebin the data because there's a tendency to supply small angle scattering data with way too many data points, which takes far too long to compute. Therefore, within the data range, the data is rebinned, in this case, to 100 data points. That also gives us better uncertainty estimates, as we can now get the standard error on the mean of the data points that fall inside a single one of these bins. I've also restricted the data range. I've clipped off a few data points at the start, and I've clipped off this wide angle range. So that's what this does. And that's all for the read-in configuration. So we know it works because if it didn't work, we wouldn't see this plot pop up. We can now go to the run settings, and you see that since this is a powder and a fairly densely packed powder, I actually have used a model of sphere with a hard sphere structure factor. We still have 300 contributions. That works really for most samples that you bring in. I have, however, increased the fit parameter limits, and that's because we have a structure factor, we have some Poirot scattering here as well, and I really want to be able to model that Poirot scattering to make sure that the thing fits. So you usually want to go a little bit beyond the radius, the maximum radius set by the smallest Q value. So that's why we've done that here. There's a couple of static parameters. There's the SLD for metal organic frameworks. We have set a volume fraction of 0.3. You can actually experiment a little bit with this because if you change the volume fraction assumption, you will change the resulting size distribution. So it is a little bit sensitive to whatever you choose for your volume fraction. You cannot get both volume fraction and the size distribution uniquely. These two things are inherently tied. But this seems to work relatively well. So now we have, after all of these things, oh yeah, I should remind you that whenever you use a model, you should always set the background to 0. I think the defaults in SAS models are something, but McSAS cannot deal with that, so that background should be set to 0. Well, McSAS doesn't optimize the background, so that's why that should be 0. Anyway, that's just as an aside. You also might want to limit the maximum number of iterations, right? So you might want to say, okay, well, I want to stop the calculation either when I have fitted my data to within the uncertainties, which is when the reduced chi-square value is 1, or when I've reached 50,000 iterations. right? 50,000 attempts to change one of these contributions into another sized contribution, or when I've reached a maximum number of accepted moves. So you have 3 different options to control when to stop, but you don't actually have a stop button. So make sure you don't go wild with these. Otherwise you might test one of these things and then you'll be waiting for a very long time if your model takes a while to compute. So you can actually test this, and you will note that that this actually does take a while for this particular sample to arrive at the convergence criterion. And well, I happen to know that it will end at some point. Don't worry. However, this part of the reason why this now takes, well, at least 10 seconds or something, is because we have a very wide data range, or a relatively wide data range, and we have a linearly uniform random number generator. So as soon as you're working with broad data ranges, I actually recommend using my little secret sauce here, which is log random. The syntax of this will change in the future, but when you set log random to true, you actually change the random number generator to a logarithmically weighted random number generator. So now it's just as likely that you get picks, random picks between 1 and 10, as it is between 10 and 100. Once you do that, you will actually see that it optimizes really, really quickly. So I recommend that if you're happy with those settings, then you save the configuration and you say run config special, whatever. And then this configuration has been saved. You actually will notice now that if you go to the McSAS optimization tab, that the thing we've just saved has been pre-filled for you in the run configuration for the optimization. Now, this is the thing I wanted to show you, because it hasn't actually deleted the data from the previous demonstration that I gave you. So you might just want to select this file and say clear selected file, and then everything is fine. So we have our data read-in. In this case, it has been read in from the template and stored in a temporary file here. And we have a run configuration, which we just changed. So if we now click run McSAS3GUI optimization, it will actually run this command. It will actually tell you what command it runs on the command line. So if you want to integrate McSAS in your data processing pipeline at the beamline or at the instrument or whatever, to automatically process your data, this will give you a good clue on how to do that. All right, now all of the tasks are complete. So we are happy, right? Because everything worked. We got 10 independent optimizations. So we have 10 sets of 300 contributions, each of which is a valid solution to our scattering pattern problem. We can now do some histogramming. So I have prepared a histogram here with 3 populations. And when I click test, it will actually show that to us. So let's take a quick look, because there is something to show. One thing that is of interest here is that, you know, it's nice, but it's not quite perfect. You see this little deviation here between the measured data and the model. And that is because these metal organic framework particles, they're not actually globular, they're faceted. And while you can model many things as a superposition of spheres, for example, works fine for ellipsoids and porous structures, faceted particles have a slightly sharper scattering pattern than spheres, so you cannot actually model that with a superposition of spheres. Second thing to show is that, yeah, we actually do have a population here. The mean radius is about 40 nanometers, so the mean diameter of these things is about 81 nanometers. We have a population here. So I've just clipped off these few large particles that give us that Poirot slope. You can also see better statistics up here, right? So when we look at the first population, we actually see the mean size for the entire range, but that is somewhat poisoned by these few large particles. So when we clip those off, we actually now see a much better estimate for the mean radius. So 17.4 nanometers, and now suddenly you've got particles of only, well, slightly less than 40 nanometers in diameter. So make sure you are actually analyzing the population that you're interested in. Last thing I wanted to show was that what I mentioned before, if you change your histogramming to linear, the population statistics stay the same because these are calculated on the individual contributions, not on the histograms. But the visualization of that histogram now is completely different because your bin edges are completely different. So that's something to keep in mind. All right, I'll leave it there, and yeah, then we will go to the next example in the next video.